Hello everyone, my name is Luke Hanks, and this is my Lab 5 video for Slinky Drop. So basically what I did in this video is analyzing the motion of a Slinky, which is basically just a really long spring, and we're dropping it, and I'm just going to analyze the motion of the bottom and the interesting phenomenon that occurs there. And so I'm just going to create a model and in GlowScript, and we're going to compare it to observations through Tracker. So the results that you'll see will show that the model is fairly accurate and that the bottom of the spring or slinky stays motionless, just like in the observation. And the physics principles that I'm using, I use Newton's second law. I have the force of gravity. Reciprocity is a fairly important one in this one. And I have the velocity and position update formulas. So here's my tracker video. My calibration length, I decided the height of the man, and my initial position and initial velocity were both 0. So in Tracker, I decided to just track the motion of the bottom of the slinky. And you'll see what goes on here. Now, an interesting property of the video that I want to note here is that the video is taken from YouTube, and this recording happened at 300 frames per second, but the YouTube playback video doesn't play it at 300 frames per second. It plays it at like 24 or something. So it seems a little bit choppy, and there might be some missing data, which will be reflected in our graph later, but we'll get to that later. So here's my model. I basically just did the same thing, except I just tried to model only the bottom of the slinky. So as you can see, there's the weight force on the bottom and the spring force pulling it up. And over time, you'll see the change from when the top catches up with the bottom. There we go. All right, so here's my coding. Basically, what I did to this is I just added the weight force, negative ball m times g times j hat, and then we have the spring force. I didn't actually use the spring force formula here. You note the reciprocity that because the slinky is not moving, the spring force has to be equal to the weight force. So I just set the spring force equal to ball m times g times j hat. And then the net force was just the sum of those two forces. And then I changed the ball velocity and ball position to velocity and position update formulas respectively. And then here we have, for the time less than 1.81, we have, this is basically after the top catches up with the bottom. The only force we have here is the weight force, negative ball m times g times j hat, and the net force is just the weight force. And then it had, I changed the ball's mass to be 0.218. That's just the mass of an average slinky. So here's my data. You can see my model is fairly accurate, but as I mentioned earlier, there is some error with the frame data, how many frames per second the video is playing. I attribute that to be the error, but it's fairly accurate. And that's my lab. Thank you so much.